Hello 10a, this is Alex. I'm back with another worked example video. This time we're looking at section 3.2 on the derivative as a function, and we're going to be computing the derivative of the function f of x equals x to the 3/2 power. So, as opposed to examples from section 3.1, where we take the derivative just at a point and find the value of that, here we're computing the derivative as a function. If you take in any value, what is the function that will give you the derivative at that point? So, first, a quick review. What is x to the 3/2? Just as a reminder, x to the 3/2 means the square root of x to the third power, because the square root of x is x to the 1/2. So we'll keep that in mind for just a second as we start the problem. So the derivative, let's just remember the definition, f prime of x equals the limit as h goes to 0 of f of x plus h minus f of x all over h. So this is the definition we'll be using for this problem. And here we'll plug in f of x equals x to the 3/2. So this equals the limit as h goes to 0 of x plus h to the 3/2 power minus x to the 3/2 power all over h. And now we need to simplify this somehow, do some algebraic manipulations to let us compute this limit, because right now we have a 0 over 0. Definitely, if we just plug in h equals 0, try to use direct substitution, we'll be dividing by 0. That won't work. So we need to simplify this somehow. It's kind of a complicated expression, so it might not be clear at first how to do it, but remember, this means the square root of x to the third power. So this is a difference of square root expressions. So, as a rule of thumb, when you have square root expressions, there's a technique you can usually use, which is multiplying by the conjugate. And so here, the conjugate would be x plus h to the 3/2, and we change this minus sign to a plus sign, so that'd be plus x to the 3/2. And we can't just multiply by that, of course, so we have to multiply the numerator and the denominator by this quantity. Okay. Now, this is a fairly ugly expression, but we can do some simplifications, and we'll see why multiplying by this in particular is useful. It'll get rid of the square roots in the numerator. So x plus h to the 3/2 times x plus h to the 3/2, h, that should be an h, limit as h goes to 0. So multiply those together, that just gives you x plus h cubed. Then we have plus x to the 3/2 times x plus h to the 3/2. And then we have minus x to the 3/2 x plus h to the 3/2. So right away as we're writing this down, we realize these two terms cancel out. Don't have any more anything to the 3/2 because our last term is x to the 3/2 times x to the 3/2. That's minus x just to the 3. So our numerator is clear of any of these fractional exponents. That's very nice. Our denominator is still kind of ugly. Nothing we can do about that for now. Okay, so that's just copying down the same denominator we had. And now, all right, what else can we do to simplify this? We still have this 0 in the denominator. We want to cancel out this h, is ultimately our goal. In all of these compute the derivative using the limit definition problems, canceling out this h that you start with in the bottom, that is your main goal. And that means you need to factor an h out of everything on top. Well, right now, it's not clear how to factor an h out of this, so we'll keep expanding and hope that something becomes clear. So x plus h cubed, I'm just going to use a shortcut that I know. You could FOIL this all out, but that equals x to the third power plus 3x squared times h plus 3x times h squared plus h cubed. If you don't believe that's what x plus h cubed is, write it all out. You'll see that is what it is. And now we'll keep the denominator the same. It takes a long time to write. And now things are starting to come together. We have a plus x cubed and a minus x cubed. So those cancel. And at this step, everything in the numerator has an h in it. So we can factor out that h, which was our goal this whole time, to factor out that h and cancel it with the h in the denominator. So let's do that. Let's factor out the h. We have 3x squared plus 3x h plus h squared all over h. And now, once more, we have to write this whole messy expression in the denominator. All right, now it's time to cancel the h's. Again, this is always our goal when we're taking derivatives. It's great when we finally get to do that. And at this point, what remains this bit is now going to be continuous at h equals 0. So when you look at this as a function of h, it's continuous at the point h equals 0. So that means we can evaluate this via direct substitution or via the limit laws, whichever way you prefer to think about it. All right, ds for direct substitution, we just plug in h equals 0 into this expression. So that gives us 3x squared plus, well, 3xh, that's 0, plus h squared, that's 0. And on the bottom we have x plus 0 to the 3 halves plus x to the 3 halves. Right, perfectly well defined, not dividing by 0, so plugging in here worked. And what this is 3x squared over, we have 2x to the 3 halves. So that is 3 over 2, x squared divided by x to the 3 halves. That is x to the 2 minus 3 halves, which is x to the 1 half. Or we could write that as 3 halves squared of x. So both of these are perfectly good ways to write your final answer. And with that, we're done. Thanks for watching.